see. So can you hear me? Yeah. So I will talk today about pervasive model adaptation and what we understand about pervasive model adaptation is basically the integration of planning and information gathering in dynamic production systems or in all kind of manufacturing systems. That work was jointly done with Johan Lee and by myself and Johan de Cler at the Palo Alto Research Center. Okay. Let's see. Can I use this one? Ah. Okay. 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 Let's start again. So today we'll talk about pervasive model adaptation and what we understand under pervasive model adaptation is basically the integration of planning and information gathering at dynamic production systems. And that's joint work which we did in our group at the Palo Alto Research Center with Johan Lee, Lukas Kuhn, which is myself, and Johan de Cler. First of all, I would like to give you an outline, and I will introduce the kind of systems which we are working on and what we are proposing to work on also in the future. And I will give you a motivation why model adaptation is actually required in those kind of systems, and I think generally in planning systems. And then I will talk a little bit about model adaptation and about the information criterion which we need to actually gather information for model adaptation. And then in order to do the planning, I will talk about the search and then about some experiments and results. So first of all, let me talk about the system. So the system is basically a manufacturing line you can think of, or any kind of system where basically the planner has to deal with the hardware. And we have here, for instance, many different components which are modular, scalable. And you can think of different kind of modules which all bring their own capabilities, and then they all together assemble to a bigger, more richer system. The problem which you have is you deal basically with a lot of uncertainty, and you have many different objectives you want to optimize for. And the uncertainty comes either basically by nature, where sometimes you throw the dice and you can't really say where the uncertainty, how the outcome will be. But sometimes the uncertainty comes really by that our models are not good enough. And I will talk a little bit more about that later on. And basically what we try to do is to optimize for throughput and have the shortest planning time. And so one system which was well introduced beforehand is basically the tightly integrated parallel printer, which is a roller coaster for ants in some sense, because you have paper feeding in on the one hand side, and then you have many different print capabilities. So you could think of that you have maybe a black and white printer, a color printer, and some other capabilities along the paper path. And then the paper is basically traveling in the machine, and then we have to decide where we have to route it to, and then bring it to the output trays. And those systems usually have a lot of uncertainty because, as you know, even so Xerox doesn't really like to talk about it, those systems jams quite a lot. And so what was done before it came there was basically planning and scheduling for those kind of printers. So the problem is that you have a machine model and at startup time, and what you want to do is basically at any given time, you have already sheets in the system and you have a machine state, and you want basically to construct a plan which is capable of finding its way through the machine, reaching all its goals, but not crashing in any other sheet. And then overall, you want to maximize the throughput. So this was basically done before I came there, and it actually nicely works by now. And so what we can see here basically is the printer in action, and it's routed through a couple of sheets, which we can barely see on the schematic down there. And so basically one of the problems is that this is also about the longest we got it actually to run. And this is what got me interested in why do we build this gigantic, really super cool prototype and then can't run it over a longer time? What is really the issue? Is it a software issue? Is it really some issue which trickles up from the hardware? And the problem turns out that the models are only as good as we design them. And so as you have such a nasty hardware, it's really hard to go in depth in there and understand the complete dynamics of the system. So what happens more often is basically that the system jams. And one of the difficult aspects of having the system jamming is that the system actually has non-local faults, meaning that, for instance, you have the cause at some point and you jam somewhere else. So that might be, for instance, the first time when you reroute the paper and you have a scuff mark already, which is okay if you go straight, but then further down the path you jam. And then the first thing how we actually addressed that was by replanning. And then we could run the system about like half a second longer because it's really fast. So it jams up then just somewhere else. And because what we actually do with the replanning is we only replan about this particular component because that's where we observed the jam. And so we got some more thinking about that, and what we actually thought would help is if we do in-depth analysis. And there are two parts to it. One is basically doing diagnosis, and the other part is doing model adaptation. So the work about diagnosis I will not talk about. That was presented a year ago. But I will talk a little bit about model adaptation. And so in typical planning systems, you have the model, and you don't really assume that there need to be any changes in the model. You may assume that there is some uncertainty, and how this is usually handled in hardware is basically that you have a control level which scopes with the uncertainty. But if you have such a printer and you don't only like to print one sheet and you're happy if you succeed with that plan, but you actually like to deploy the print and have the print around for a longer period of time, your system is actually changing over time. So if we have this static knowledge about the system, what we need is basically that the system adapts, that the model adapts to the system as the system is evolving. So there are basically two reasons why a model can not be as accurate. One is that it's really hard to get it right in the first place. Then one other thing is that components might drift over time. And so one way, as I was saying, how we can scope with this is if we look at the schematic down here, then we just leave a lot of slack time in between the sheets. And so if we get them far enough away from each other, then at least they don't run into each other if we don't exactly can predict where they are. But we can do better about this if we actually try to have the model tracking the system as the system is evolving. And so what we need is, one thing is model adaptation, and the other thing is that we actually come up with informative plans. So model adaptation, basically, there are three very high-level main things how you can do it. One is that you put enormous amount of sensors in there, and then you can basically measure each individual action and just update the model accordingly using some model adaptation scheme. The problem with it that it's really expensive if you put so many sensors in there. The second thing is that you can't just monitor the system. You, for instance, have a couple of sensors, maybe only one at the output, and you only monitor what this sensor gives you, and then you do the backward accounting. Basically, okay, if I have this accumulated delay, what would actually be the individual actions? How do I have to adjust the parameters such that they will actually fit what I've observed? The problem with passive adaptation is that since you are not involved in selecting the actions which will actually give you the most information, is that you get only very limited information. So if you do explicit model adaptation, then in most cases what you have to do is to hold the production and then come up with a suite of test plans, for instance, which you constructed beforehand, and then run them all through adjust the system, and then rerun all your production plans. What we wanted to do is basically to have a system which only needs a few sensors, has ideally unlimited information, and be able to continue production while it's actually finding some more information. So we call this pervasive model adaptation, which basically means we want to generate plans in a way that they're partially optimized for adaptation. And we use the flexibility in plans. If there are, for instance, more plans which lead to the same goal, then we would pick the one which is more informative. So we try to maximize long-run productivity by trading off some of the short-time goals, meaning that we can reach the goal maybe not as fast as we could reach with an alternative, but we will actually learn something which will help us in the long run. And there are a few assumptions built in here. One is, for instance, that you need to be able to have informative plans intersecting with production plans. That might or might not be true. Because if you have to cut open your product, for instance, to look inside to predict something or to observe something, that wouldn't help. And then the other thing is that you need to be able to scope with uncontrolled failures, basically with jams. So if you print something and it jams a couple of times, at least it learns something over time. Whereas if you would do the same thing with planes, and it would actually, you would say, okay, let's adapt the system, let's go in the ones where it's actually in the parts of the system which are informative, then and the plane would crash, that would be very nasty. So a little example to that is, let's say we have the plan up there in the system where we actually go in the system, go to one of the print engines, and then leave the system and observe some kind of delay. So what we could do is, now we suspect all the modules on the way. What we could do actually is construct a plan which will then only go through half of the components or actions, and then we are able to narrow down the suspected set, and we can do this again and again. So if we now look at the overall architecture, there are a few things which need to be done. One thing is we need to be able to take observations, so we have some sensor maybe at the output. One thing is that we need to be able to learn, but in order to learn, we also need to have an information criteria that we actually can derive plans which are most informative. Because only if we provide information, we are also able to learn. And if we have the information criteria, we need to be able to search for such plans. So model adaptation, we can quickly look at the dynamics. Here in that example, we look at action durations, which we can update. So we have theta, which is basically the action duration which in the step before that plan. And then there's some Gaussian noise. And we assume that each time when we use a certain component, we have an extra delay, and each time, or an extra drift in the dynamics model. And each time when we don't use a component, it's basically there's no drift. And the drift is due to degradation. So we can use this dynamics model, and the observation is basically that we accumulate all the action durations plus some random noise. And so we can rewrite this, and what's only important here is basically that we have this h value, which basically is an indication of which of the actions are in that particular plan and which of them are not in that particular plan. So then we can take off-the-shelf a Kalman filter, and what's only important about this slide is that the Kalman filter, how it works on a very high level, is that we can predict what the state would be if we have no observation after we executed that plan. Then we can account for the observation which we actually got and do that update and iteratively learn the parameters and estimate them in the right way. What's also nice about the Kalman filter, it's not only updating your model, but it also gives you some a covariance matrix, which gives you some confidence how good you are doing. And we use this covariance matrix later on. So if we can do the model adaptation, then now the information criteria comes into play. And what we do is we use the trace of the covariance matrix for confidence level, for our confidence level. And so we can use this last update equation and reformalize it into the second equation And then what this basically says is, if this is the trace which I had before, and this will be my new trace given that I run through this update, then I have to maximize that last term in order to get the minimum uncertainty, because the trace is basically a measurement of the uncertainty you have in the system. So what this will then be about is we need to find plans which minimize that nasty term down there. And I will talk a little bit about that. So a small example, basically, intuition is that if you have a system with two components and you know nothing about the system, then what you really want to do is to run as many through them as possible. If you actually have already gathered some knowledge and they are, for instance, positively correlated, these two components, then you want to test them individually. And this is sort of mirrored here in those slides. It depends on the current knowledge what would be the best next plan. So if we now have this information criterion, we want to optimize that particular equation, then we need to have some search for that in order to derive the right plans, which actually will exercise the system in a way that we will actually learn the most or gather the most information. So this equation looks really nasty, but it's actually because the h value is a binary vector, it's really fastly to compute because it's really only taking the row sums or the column sums. But there are a few challenges with this. One of the problems is that if you have an optimization criteria like this, then it's not longer order preserving, meaning that if you gather more action, then it's non-monotonic in the sense that if you have no actions and you add some actions, you learn more, but there's a peak where you basically fall off, and if you then gather too many actions in your plan, then you lose the information. And so one other thing is that it's not decomposable onto the action level, meaning that you can really only say, if you look at the entire plan, what you potentially will learn. But this individual action will not really be informative by itself, or you can't say what the content is of information you can learn by a particular action, because it can well be mirrored by others. It can be basically blocked by others. So what we did is we have a two-step approach, and we have a greedy algorithm, which is this info collect, where we basically take the, which we use then as a heuristic. And this info collect doesn't consider any path constraints. And then we use a best first search basically with this info collect in order to run our search. So offline, what we need to do is we need to compute 3 sets for each action, and these are grounded actions. And what we compute is the successor set, meaning all the actions which I can reach, then the predecessor set, all the actions which I can basically reach in the opposite direction, and then all the actions which I'm not connected to. And then online, what we do is we use a best first search, which is guided by this info collect, and at each single step, we preset the age. Basically, what we do is we take this age, which tells you which actions will be in the plan or not, and then we annotate everything with 0, which is unreachable, given a certain prefix. Then we annotate everything with 1, which is already visited by this prefix, and then we look at all the things which we can still reach. What we do then is that we find the next best undecided action. Basically, we have this prefix, and we could potentially reach all of them, and we get rid of all the path constraints, and we just look at the one which would be the next best, which should be in my plan. And we do this greedy algorithm, we perform this greedy algorithm over and over again, and each step what we basically do is, okay, if that's the next best, then put it in the plan, and then get rid of all the ones which we can't reach, if that would be in the plan, and update the h vector accordingly. And we stop by, at the moment when we can't find any action which actually will improve the performance of that information gain. And so after we did this, we use the best first search, and that will guide us through the search space. then the way how we get these two things together is basically by multi-objective planning, that we just have the one for production and the one for adaptation, and the alpha is the health index, which basically tells you how bad you're doing in terms of uncertainty and then what you want to do more. I will quickly talk about two experiments we did. One is on pure information gain, and the other thing is on long-term productivity. And the experiment was set up that they all use the same adaptation scheme, and we have set it up to have 6 actions drifting in their action delays. And then we run the example 200, for each experiment we run 200 times. And it's always planning, then executing, observing, and updating 100 circles. So what we can see here is that if we have on the y-axis, we have the uncertainty growing, and here we have over time. If we do regular production, it will just really shoot up because we don't care about the estimation. Another thing what we can do is basically do uniform distributed search, that we just say, okay, let's try to use everything about the same amount of time. And that will give you some improvement. If we do pervasive model adaptation, where we actually do look at the constraints of production, then we do almost as good as if we get rid of all the production constraints. And so we are able to learn a lot, even so, while we do the production. So now one question comes into play, of course, is how fast can you do this? Are you really fast enough? Because if you learn just with each plan really good, but you're much slower in order to perform that, then it would actually be better to hold your system and do explicit knowledge gathering. So we looked at this in regular production. These are just some indications. The fastest uniform is also quite fast. Then pervasive production is the slowest. And then dedicated testing, where we only do the best for the model adaptation but don't care about production, is also reasonably fast. And we have a maximum uncertainty at any given point, which basically means if we reach this, we can't produce anymore because the system is off in the wild. And we compared a few strategies. One is regular production together with dedicated, where basically we do regular as long as possible, and as soon as we lose the system in terms of uncertainty, then we just do the best for model adaptation without actually caring about production. The same with uniform, then pure pervasive, where we only run pervasive, and then regular and pervasive together. And what will happen is basically that if we look at the uncertainty, they will all sort of shoot up to that maximum threshold and then bounce along these lines. And what we can see is that pervasive is actually staying far below the line. So the next question is, of course, is that really a good thing that it stays so far below the line? Because now it's sort of overachieving. We told the system we can scope with this much uncertainty, and we keep it actually much more down, and we lose some of the production. So if we look at the graph below here, is what's the way the best strategy is that you do your regular production as good as you can and as fast as you can, and only really care about model adaptation together with production if it's necessary. And that's sort of the intuition behind that. So as a summary, what we did is basically pervasive model adaptation, where we optimize plans such that they will gain the most information to estimate parameters. And those parameters can be slack time in between sheets in terms of scheduling. This can be action duration, that can be pressure, and that can be all kind of parameters which you have in your planning model. And we derived this information criteria, which we need to optimize in order to do that. And we have some experimental results, which basically give us a speed up of 8%, which is quite a lot in our application, and that depends from application to application. So if I'm still allowed, then I would show a very last movie, which is only a couple of seconds. And what we see here is it changes from regular production, then we insert a delay, and then it will try to figure out the delay by having some funny plans, and it will then, as soon as it has figured out where the delay is, update the model and go back to regular performance. That's a very good question. So what we have done is we have put the work about the pervasive diagnosis on the printer, and then we have a smaller version of it, which we actually were able to put this one on as well. The reason why we could not test that on the bigger one is because the bigger one is gone since the beginning of the year, unfortunately. Xerox didn't like to fund it further.
You mentioned diagnosis at the beginning, and obviously the estimation of the parameters that you're performing is predicated on the assumption that the printer is operating in a particular mode, and in particular that the components are operating normally. And if that assumption is violated, then it strikes me that you can incorrectly adapt your model because under the assumption that the components were operating normally. Now maybe in this particular example, faults in components manifest themselves so extremely that you would immediately know that something was faulty and not run into that difficulty. But I was wondering whether you could talk about the bigger picture, which you mentioned at the beginning, which is of course diagnosis as well as parameter adaptation or model adaptation.
That's a very good question. One thing which is leading all this work, meaning the diagnosis and also the model adaptation and a learning work which we do other than this, is that we really would like to have the model tracking the system, and then we're able to look at the model and identify if it's still a valid system and if we should still use the system. And so by having the system, by having the model tracking the system, then we can always decide if we are still able to actually print something or manufacturing something. But most of the systems right now, they track the model. What happens is that we have some model-based system in place, and then we have the technician to fine-tune the system such that it reflects what's written in the model. But the other way around would be the more preferable for us.
Needs to be modified is pretty good. I mean, it's that most of the models are incomplete to begin with, and I love the fact that you're trying to adopt them as time goes on. The one question that I have is the more, I guess, more wishful problem would be that I don't even know where my model is incomplete. It seems as if in your case, you know that certain parameters may not have been properly specified, and so you're tracking them. In other cases, I might even know, for example, in terms of more action, precondition, effects kind of models, I might find out that certain actions that I'm doing are not having dedicated effects. Mm-hmm. And I need to be able to figure out why that happened. And clearly, the overall framework seems to be relevant, but I'm just wondering whether you could talk about things like informative plans in those cases too. You know, you seem to be getting a lot of leverage in this case because you had the Kalman filter sort of figure out the parameter which tells you exactly where the incompleteness is. Yeah. If you have much more incompleteness, or you have an idea.
So what we have been working on is basically, here we only track parameters. So we assume that the model actually, by its structure, is correct, but the parameters are off. There's other work which is ongoing right now where we actually learn the structure. And so one thing which could be interested is not learning the structure of how the faults relate to each other, in the sense of you first have to run through this component and then have to run through this component in order to get to a fault state. And one other thing which you were relating on, if the basically effects of certain actions are really there or not. And so this can be basically also done with a state estimation where you basically track the system, and if you would have some way of observing some variables which are related to your effects in the actions, then you could track if they're there or not. And then also, if you can't track that after each individual action, then you would need to do this backward accounting of if you have this like some effect is missing in the goal, whereas your plan was actually participating in making it true, then you have to figure out which of the actions which would make that effect true would actually cause that problem. And so there's a lot of work going on right now also in terms of a more in-depth diagnosis, where it's really about reasoning about the root causes, having intermittent faults, having structure, and that's partly what we incorporate right now.
Any more questions? Oh,
The relationship between the model parameters and the planned parameters is quite, planned parameters and data is very specific here. What one may wonder for is a more global model that describes both the functioning of the system as well as the planning, the general planning specifications, in order to address the aspects of information gathering in a general framework corresponding to the kind of representation and planning you have. So, have you thought about that? And do you consider that your work can be translated to some other kind of information gathering and other kind of models than the specifics of this algorithm?
So this was a very specific example, of course, and we put the example together where we actually only track action durations. But as I was saying before, if you have some model, whatever models what you're interested in, and there are a few inherent uncertainties, like in terms of which are the effects which are actually really belong to that action, or for instance, you would be interested in learning probabilities, like which is the action which will maybe cause a fault or not, or which is the action which actually caused the fault, and then all other things might be structure in the model. So for instance, you maybe have a path in your planning system, but that path is not there in the real system. And so those are all things which we generalize to, which I haven't had the possibility to put them all on the slide.